Introduction. Graph theory, a branch of discrete mathematics, is the study of mathematical figures involving nodes or vertices, edges and arcs which interconnect the vertices forming a figure. This seemingly simple theory helps us map many complex problems as we can associate various objects, people, places with the nodes and arcs. In this project, we will see how the graph theory is used for navigation and calculating shortest path between various nodes considering factors impacting the decisions. Application/motivation. The concept of graphs have wide-ranging applications in various fields, but one of the most eminent uses of graph theory still remains in mapping and navigation. Algorithms such as Dijkstra's algorithm and ASDA's search algorithm come in handy while designing mapping systems and finding shortest path between 2 points as such used in Google Maps, GPS devices, food delivery apps, etc. Dijkstra algorithm is used to find the shortest path from the origin to the destination. ASTA algorithm is a 2D search algorithm which searches for the shortest path between the initial and final state keeping in mind the various obstacles and barriers. Both the algorithms seem similar, but the Dijkstra's algorithm explores all the paths possible between 2 points which works well for smaller graphs, whereas the ASTA algorithm uses a heuristic function which uses a priority list to give higher priority to nodes that are supposed to be better. Keeping in mind the above algorithms, we seek to implement a navigation system at small scale to formulate and implement an algorithm that helps us walk through different locations in DA/IICT, covering minimum distance in the process using graph theory. This is the map of DA/IICT. Transforming the map into a graph, we have Dijkstra algorithm. Dijkstra's algorithm is an effective algorithm proposed by Edsger W. Dijkstra. It is one of the greedy algorithms used to optimize and find the shortest path between nodes in a graph. The algorithm keeps track of the shortest currently known distance from each node to the source node and updates these values as shorter paths are found. Algorithm. Mark all nodes as unvisited. Create a set of all unvisited nodes, called an unvisited set. Assign a tentative distance value to each node. During execution of the algorithm, the tentative distance of node V is the length of the shortest path ever detected between node V and the starting node. Update the starting node as the current node. For the current node, consider all unvisited adjacent node and calculate their tentative distance through the current node. Compares the newly calculated interim distance with the distance currently assigned to the neighbor and assigns the smaller distance. After reviewing all unvisited neighbors on the current node, mark the current node as visited and remove it from the unvisited set. The node you visit will not be checked again. If the destination node is marked as visited, the algorithm is finished. Otherwise, select the unvisited node marked with the minimum interim distance, set it as the new current node, and return to step 3. Example. Let's try to find the shortest route from new boys hostel, O, to girls hostel, D. Step 1. As illustrated, this operation uses a greedy algorithm approach. It finds all the nodes' shortest path starting from the source node. First, we choose O and mark it as visited. Step 2. Update distance values of its adjacent vertices, for example, J, L and M. Distance of J, L and M were updated as 6, 4, and 1. The following subgraph shows the vertices and their numerical values, showing only vertices with approximate distance values. Step 3. Pick the vertex with minimum distance. The vertex M is picked and marked as visited. Update the distance values of adjacent vertices of M. The distance value of vertex L and A becomes 3 and 11. Since the previous shortest distance of L is greater than 3, the new shortest distance of L becomes 3. Step 4. Pick the vertex with minimum distance. The vertex L is picked and marked as visited. Update the distance values of adjacent vertices of L. The distance value of vertex J, I and K becomes 7, 8, and 1. Since the previous shortest distance of J is less than 7, the new shortest distance of L remains same, for example 6. 5. We repeat the above steps until all nodes of the given graph are not visited. Finally, we get the following path graph. Step 6. We see that the shortest distance between O and D is 14. Limitations. To find the solution to real life, in the open world, the number of nodes are almost limitless or uncountable, and this algorithm may fail due to increasing time and space complexity. And that's where the ASTA algorithm proves to be useful. ASTA algorithm. ASTA search algorithm is one of the best graph search and method search algorithms, designed primarily for weighted graphs. Highly preferred because of its completeness and its overall efficiency. A better and efficient version of Dijkstra's algorithm. This algorithm depends on 3 functions. Gn represents cost of traversing from one node to another. Hn represents heuristic approximation of the node's value, which simply means approximation cost from the source node to the target node. Fn represents the final cost. Fn equals Gn plus Hn. The algorithm goes as shown below. 1. Initialize the open list. 2. Initialize the closed list. Put the starting node on the open list. You can leave its f at 0. 3. While the open list is not empty. A. Find the node with the least F on the open list, call it Q. B. Pop Q off the open list. C. Generate Q's 15 successors, nodes present in our map, and set their parents to Q. D. For each successor. I. If successor is the goal, stop search. 2. Else, compute both G and H for successor. Successor.G equals Q.G plus distance between successor and Q. Successor.H equals distance from goal to successor. This can be done using many ways. We will discuss them in next slide. Successor.F equals successor.G plus successor.H. 3. If a node with the same position as successor is in the open list which has a lower F than successor, skip this successor. 4. If a node with the same position as successor is in the closed list which has a lower F than successor, skip this successor, otherwise, add the node to the open list end, for loop. E. Push Q on the closed list. End, while loop. Example. Let's try to find the shortest route from college main gate, A, to canteen, H. 1. First, we start off at initial point A, and push it in the open list. Then, let us move A to the closed list and check the possible nearby options and move them to open list. 2. We have B, M, and D as feasible options. As B is the nearest point and has the least G value, it has the least F value, so we now move B to the closed list and check the possible nearby options and move them to open list. 3. We again choose the path with least F value, which is K. After K, the least F value option is H, the goal. Even though we reach the goal, we still don't know if we are finished yet. 4. We move H to the open list and check the open list for the least F value, which is H. But, in this case H wasn't the least F value option. We will continue the process till the goal is reached. Implementing the solution. From this, we learn how Dijkstra's algorithm and ASTA's search algorithm helps us in understanding navigation using graph theory. Now, using these algorithms we will try to enact this using coding softwares. Now we are going to implement the following algorithm by programming a code in C++, intertwining the basics of this course as well as IT206 course, data structure using OOP. We will observe how the following input is recognized and how the whole algorithm is applied in order to get the shortest routes. Here's the implement of above algorithms in C++. Commercializing the project. We can commercialize the project with enough funds into a software used for navigation, deliveries, etc. Google Maps API can help us manipulate interactive maps and customize them, while satellite image processing will help us in implementing highly detailed orthoimagery, providing us a pictorial image of the area of interest in our software. For example, a delivery or ride-sharing service will use this to show driver routes, while navigation systems will use it for displaying shortest time routes. We design an app by choosing a map provider, configuring plugins, customizing maps, displaying user position, adding address fields, set up routing and display route information. To administer this into a fully fledged operational computer software need an extensive knowledge about JavaScript, JSON, data processing, data collection, etc.